Giant Panda Conservation Unit and is the General Scientific Director of Cocha Cashew Biological Station in the Peruvian Amazon. His work focuses on the conservation of species in their native habitats with the emphasis on reintroduction and translocation programs. Today he will talk to us about captive breeding, reintroductions, and translocations as tools to rescue small populations.
Thank you. Thank you for inviting me. It's a pleasure to be here, to be, I say, back in Davis, because I did my graduate work here at the Animal Behavior grad group, so it's always good to have a reason to be back. So today I'm going to talk about this topic here, captive breeding and reintroductions. I'm not going to go into the whys, whens, and those sorts of bigger issues that I think will probably be part of our later discussions. But this is going to be more of a how-to, some of the developing a toolbox to work to recover some of these species or arrest the decline of some of these species. And I think it's important to point out in doing conservation that we really need to start with the conservation problem. Sometimes we just go study endangered species because they're endangered. And the approach I like to take is not just a trial and error approach, but to try to identify some unifying theoretical framework, particularly emanating from behavioral ecology, because that's my background, and then apply it to test hypotheses to see if we can develop better conservation tools. Like Dr. Wilkove here, I was a little bit surprised and pleased to see that there was going to be a special symposium on species conservation, because I do think that we've gravitated away from that focus, particularly in the conservation NGO world and academia. The focus on the species and the organism has become the new black box, and we're often looking at levels higher and lower than the organism of the species. So then one goal maybe of the symposium can be to get a little more respect for species conservation again, at least get it back on the radar a little more than it has been in the last decade or so. There's a lot of reasons that we want to work to save species, and Aldo Leopold identified it quite well a long time ago, and that's that removal of species from the system can have lots of unforeseen consequences. That thought, I think, became passé for a while, but it's coming back. It's coming back with harder evidence, more rigorous evidence that there are these species that have disproportionate effects on ecosystems. So moving into the meat of my talk, I'm going to go over a few of the tools that we've developed. It's kind of a grab bag of tools that we've developed over the years to deal with specific problems. One is, of course, the failure of animals to breed when you're trying to establish a conservation breeding program. And in this case study, I'm going to talk about using the signaling system, and that is the pandas signaling system. That's also why pandas are so popular, because of their charismatic anal gland.
Thanks for telling me what that was. It's hard. Whoa.
I didn't appreciate the panda bear comment earlier either. They're actually a great umbrella species. But so back in the day, we had a captive population that was not self-sustaining. The birth rate did not exceed the death rate, and we threw up a lot of hypotheses, and one of them was communication breakdown. We knew that pandas use these scent marks in the wild to communicate with one another, but we really didn't know how this scent signaling system was used. So over the years, we devised a number of experiments to test, basically what kinds of information pandas extract from scents and how do they use that in their courtship and reproduction. So and here's kind of the laundry list of things that we learned about olfactory communication in giant pandas. And I think the end result is that we found that it actually was a very sophisticated communication system. Pandas can identify individuals, sex and reproductive condition of the females. They're just involved in mate preferences. They can determine the age of the signaler. Also, these handstands, for example, are signals of competitivity in males. We know how long these signals persist in the environment, how long pandas remain responsive to them, and quite a few other things. But the point for today being is that we took some of this information and we worked with the managers very closely at the breeding centers in China and changed the way that the animals were introduced to one another. And we developed a method where we exposed them to the scent of the opposite sex at the right time to turn down the aggressive tendencies and crank up the sexual motivation, and with quite a bit of success. More recently, we've also looked at the acoustic communication in pandas, and we found more or less a similar story there. And we took this kind of information and we developed a decision tree that we gave to the managers on deciding, when and how to place pandas together to get them to breed. And very long story short, we went from just a handful of pandas mating naturally to over 90% of the pandas at this Sweihan breeding center where we're working were mating naturally. And this is the end result. Lots of pandas. Last year, we reached the critical threshold that we had identified of 300 captive pandas in the population for self-sustainability. And if you don't believe pictures, you like graphs that got that. So one of the other tools that we've had to develop in conservation breeding is this idea that mate choice can actually affect some of our conservation results negatively. And there was, for quite a while, there was a lot of discussion, a lot of writing about the role of mate choice in conservation, particularly in reproductive skew, but nobody was doing anything about it. I'm going to share with you just one short case study where we did manipulate mate choice for a conservation purpose. And this is the pygmy loris, which is threatened. And of course, these animals are managed to maximize outbreeding. But of course, there are problems with these programs at times. Failed matings, sometimes the female's choice runs counter to the stud bookkeeper's choice. And of course, reproductive skew and low effective population size. Oops. So our hypothesis was maybe that these smelly, solitary lorises use odor cues to select mates. And again, long story short, I think this might be the largest magnitude of mate preference trial that I've seen in the literature. But we got a walk-in effect by simply familiarizing the female with the scent of a particular male. We did that systematically and then giving her a choice between a familiar smelling male and a novel smelling male, and to very large effect. So the next topic that I want to talk to you about is reintroductions and translocations. And I think this is becoming increasingly important. Managers are moving animals around on the landscape more than ever. And so in this era of assisted migration or proposed idea of assisted migration in the wake of climate change, I think it's going to become a tool that's used more and more. I would say that perhaps we haven't developed enough knowledge. The field of translocation biology, reintroduction biology, is really just getting its legs. So I think we need to work on how to translocate these animals. So there's a number of variables that can affect the outcome of translocations and reintroductions. I'm going to focus on the post-release environment, which I think until recently has received less emphasis in the past. And here's some of the variables that can affect post-release. And I'm going to talk about a few of these. Social environment, the idea of habitat requirements and limiting resources in the release site. And then a little bit about post-release dispersal and habitat selection, including conspecific cueing or attraction and natal habitat preference induction. So first, the role of the post-release social environment. This work was done by Deborah Shire as her PhD right here at UC Davis with black-tailed prairie dogs. And at the time, managers were relocating prairie dogs and trapping and releasing them elsewhere. And Deborah decided, since they're highly social animals, to try to identify family groups and release them as family groups. And she got a 500% increase in survival. Another species I'm going to talk to you quite a bit about today is the kangaroo rat, particularly the Stevens kangaroo rat, which is an ecosystem engineer. And by the way, I think when we choose animals for species recovery, we should be selective. And one of the criteria that we ought to be thinking about is working with species that have disproportionate effects on the ecosystems. So this is also work done by myself and Deborah Shire. And we took this idea from a very social animal, the prairie dog, and we got to thinking about a rather non-intuitive question with a solitary, territorial, and aggressive species, that they live in neighborhoods and they have relationships with these neighbors, even if they're nasty neighbors or conflictive relationships. And so what we did a test where we did controlled translocations either with sort of replicating the geometry of the neighborhood with familiar neighbors or not. And we thought, well, we might get a little boost in survival, some interesting behavior. And we were quite surprised. We got fairly dramatic effects. We got 3 times the survival rate for the neighbor translocated groups, and also much higher reproduction. So that a year later, the neighbor translocated groups had outpupped the controls 24 to 1. So that's a pretty significant effect, and one that, frankly, the managers thought was kind of a silly experiment to begin with. You know, these are solitary animals, who cares about the neighbors? So, and this also, by the way, is the first time, to our knowledge, that anyone has shown a fitness effect of social relationships on a solitary animal. So the behavioral data were also very enlightening. What we found was that the neighbor translocated groups foraged more, fought less, traveled less, settled closer to the release site, settled sooner, and established their burrows sooner. So the idea here is that they had to deal with negotiating new relationships with new neighbors and did not prioritize the things that a translocated animal needs to prioritize, avoiding predation, getting their burrows, and not moving so much. Another example I'll give you is from the desert tortoise. And one of the things we're looking at with the desert tortoise is resources in the environment that might be a limiting factor, particularly for a released tortoise. And one of the proposals we came up with is these caliche caves that they use. They're deeper, they're cooler, they're moister than the burrows that they have to excavate their own burrow. So we just simply released half of the tortoises in washes with caliche caves and half up on the flat, where they had to dig their own burrows, and trap them. And found that we did get quite a big effect on movement. And moving post-release dispersal, or post-release movements, is one of the best predictors of mortality. So the more an animal moves, the more likely they are to die across species. So we do a lot of manipulations simply to dampen that post-release movement. This is an early study that these are new data, but what we're finding then is also we found an effect on survival. The ones that were released near the caliche caves did have a higher survival rate, although it's a very small sample size at this point. So, how am I on time?
You're at
7 minutes, okay. So I'd like to delve down a little bit more into this problem of post-release movements. If you think about a translocation, it's really a forced dispersal. You're relocating the animal. These movements after post-release, I should mention that this is some work that I did with Judy Stamps, who's here in the room. She was the lead author on this review paper that we wrote. But these post-release movements can exceed the species-typical movements during dispersal. This is a high-risk, high-mortality period. And the distance traveled, again, correlates with mortality. And too often, when animals are released, they move out of the protected area and basically get themselves into trouble. So here's an example from the Stevens kangaroo rat. You can see we have tiny transmitters that we attach to this guy. We're going to rename them pocket kangaroos so that people like them more. And here's a good example of a negative correlation with distance moved and survival from this release. So some of the risks for long-distance dispersal is our failure to settle, even in suitable habitat, the energy expenditure, poor foraging success, exposure to predators, conspecific conflict, increased stress, and accidents. So now another topic that's going to be near and dear to Judy Stamp's heart is conspecific cueing and habitat settlement. Animals will use the presence of conspecifics as cues to habitat quality. That's work that's been well established over the last 20 years or so. And this is seen not just in social species, but also in less social species. And the preference is to settle near the occupied territory of another individual. And this has recently become much more accepted in wildlife management and conservation, I would say, for the last five or 8 years, as a dominant factor influencing where animals settle in the environment. And here's a few cases where conspecific cueing has been used in conservation action. In one example, decoys, fairy terns were used in models to establish a new breeding colony, and playbacks have been used to facilitate territory settlement in several species. So this is encouraging animals to settle in areas that they otherwise would not have settled, so unoccupied habitat. And next I'd like to give you a brief overview of a case study that we did with black rhinoceros. Quite easy to translocate, as depicted in the picture. The South African government was already doing this. We didn't have to do that part of things. There were problems associated with these translocations, such as unpredictable dispersal after release, and also there's a lot of fighting and mortality associated with fighting, and sometimes stress and something that we would loosely call panic upon release. So we decided to test the conspecific cueing hypothesis by manipulating some of the signals in the environment. First, we had to study those signals, so we did some studies to try to understand what dung and urine mean to rhinoceros. And we developed a design of a study where we basically created virtual scent territories with their dung and see if we could affect the settlement patterns of released rhinos. This is how one disperses rhino dung. If there's a road, otherwise you have to backpack it out there. So the results were very interesting. This is just one animal's movements. But if you follow the red line here, do I have a pointer of view? So this animal was released here, and it's settled sort of adjacent to and overlapping where we had dispersed the dung of another rhino. And in this particular study, we had 17 of them, and all 17 settled adjacent to and slightly overlapping the dung of another rhino. So we found that we could manipulate their settlement patterns on the environment. And since we've done this work, the managers of these reserves have sort of taken on this job of slinging dung for us, and they're continuing to use this strategy. We also did basically the same test again with our kangaroo rats back in Riverside County. This is again Deborah Shire's work, and we found again that they were more likely to settle at the release site if we spread their scent at the release site. And we got a little bump in survival, at least for the first 3 months, but not a whopping effect, and it wasn't one that lasted over time. So the other mechanism that animals can use to settle to guide their settlement decisions in the environment is natal habitat preference induction. I think I've used Judy's name too many times, so I'll just ignore the fact that this is her work too. But dispersers will often prefer to settle in habitat that's similar to their natal habitat, something like imprinting. And they're basically using quick and dirty rules of habitat quality. Survival to dispersal age is an indication that the habitat was suitable, in which in the natal habitat was suitable. Or it could be a performance-based decision. That is, experience in habitat A increases performance in habitat A, and that may guide dispersal and habitat selections decisions to settle in that habitat. So it's important to realize here that habitat selection is an individual's, not a species decision. What is suitable for one animal may not be suitable for another. And it's what animals perceive as suitable that differs. So, for example, if you're from the Great North, you might think that that's habitat, that snowy habitat is suitable, but as one who lives in Southern California, that's not that suitable for me. I see you standing up, so I'll try to expedite the end of this. So, the hypothesis here is that animals that are released or translocated might keep dispersing because they are simply looking for someplace like home, someplace like their natal habitat. Here's an example from red squirrels. Red squirrels that were captured in Scotch pine forest and which, when released, would traverse through Corsican pine forest to settle in Scotch pine, and vice versa. So they both actively rejected the habitat type that was not their natal habitat, even though one of these habitats was associated with higher fitness than the other. And in this case with caribou, but they translocated caribou from either open areas or from mountainous areas. When they were relocated, the ones that came from open areas would move to the south-facing slopes in the winter because that's where they thought the food was, and they would dig for lichens under the snow and not find much. And the ones that were from the mountains went to the north-facing slopes and ate the lichens that were on the tree trunks and performed much better and had twice the survival rate. So here's some ideas for how to solve some of these problems in a translocation context or a reintroduction context. You can acclimate them to the release site first, but that's only truly if you can really expose them to the local cues. You can select a release site habitat that's similar to the natal habitat. I think that's probably often the easiest. You can avoid creating preferences for artificial habitats in captive breeding programs. And perhaps you could even plant cues in the release environment that mimic the cues that were present in the natal habitat. So I think I'm going to skip over my last topic, which is using kind of the theme that I'm trying to develop here is that with some effort and with mixed success, we can restore some of these systems by bringing things back one piece at a time. Thank you.
In these reintroduced individuals that are dispersing more than would have been normal, do you see that also with them being less concerned with anthropogenic problems? Is that related at all to how they were captured?
Less concerned with what problems? I'm sorry.
With the dispersing farther than you would like, or is helping.
So is the question that are they dispersing so far because of something in the captive environment is?
Given that they interacted with humans more than they or an active species, does that mean they would cross roads earlier or avoid human structures less?
It's certainly in captive breeding and release programs, that's a big factor that's often addressed, and there's a lot of methodologies to reduce their exposure to humans. Most of the examples I was citing here were actually translocations, so they were wild-caught individuals that hadn't been exposed to humans. But I do think that a good example of what you're talking about comes from the black-footed ferret work, where animals that were reared in more naturalistic environments, that was more like what was at the release site, moved shorter distances and survived at higher rates. And it might be because they were the ones that were reared in very sort of more human-dominated cage kind of system, may have been simply looking for something more like where they came from. Will probably be part of our later discussions, but this is going to be more of a how-to, some of the developing a toolbox to work to recover some of these species or arrest the decline of some of these species. And I think it's important to point out in doing conservation that you need to start with a conservation problem. Sometimes we just go study endangered species because they're endangered. And the approach I like to take is not just a trial and error approach, but to try to identify some unifying theoretical framework, particularly emanating from behavioral ecology, because that's my background, and then apply it to test hypotheses to see if we can develop better conservation tools. Like Dr. Wilkove here, I was a little bit surprised and pleased to see that there was going to be a special symposium on species conservation, because I do think that we've gravitated away from that focus, particularly in the conservation NGO world and academia. The focus on the species and the organism has become the new black box, and we're often looking at levels higher and lower than the organism of the species. So then one goal maybe of the symposium can be to get a little more respect for species conservation again, at least get it back on the radar a little more than it has been in the last decade or so.
Giant Panda Conservation Unit, and is the General Scientific Director of Cocha Cashew Biological Station in the Peruvian Amazon. His work focuses on the conservation of species and their native habitats, with an emphasis on reintroduction and translocation programs. Today he will talk to us about captive breeding, reintroductions, and translocations as tools to rescue small populations.
Thank you. Thank you for inviting me. It's a pleasure to be here, to be, I say, back in Davis, because I did my graduate work here at the Animal Behavior grad group, so it's always good to have a reason to be back. So today I'm going to talk about this topic here, captive breeding and reintroductions. I'm not going to go into the whys, whens, and those sorts of bigger issues that I think